I have, for at the end of the talk, I have these very cool NVIDIA rulers on PCP board. And the people who ask the best questions will perhaps get a ruler. They used to put, they've got all sorts of, stuff like LEDs, et cetera, on here. They used to put the die traces for the NVIDIA GPUs, but now they're too big to fit onto the ruler. So anyways. All right, we good to go? We're good for the recording? Okay, cool. So, hello and welcome everyone. My name is Bryce Adelstein Lelbach. I am a principal engineer at NVIDIA, where I founded the CUDA Core Compute Libraries team, and I now lead the Vanguard programming group, which is responsible for programming language design and evolution. So my job is to make every major language a GPU language, from Fortran to C++ to Python to Rust to JavaScript. I'm involved in the leadership of many programming languages. I chaired the Standard C++ Library Evolution Group and the American Programming Languages Standards Committee. So today, I'm excited to share with you a preview of a new programming model and compiler stack for CUDA, which is NVIDIA's compute platform, that we have recently announced and will be released soon. So first, what are GPUs and what are they good for? So modern CPUs and GPUs are both general purpose processors that can run any kind of code. They differ in what workloads they are optimized for. CPUs are optimized for latency. They have more powerful cores and threads, but less of them. They have less latency to access memory and a lot more memory to access, but at the cost of lower throughput. GPUs, on the other hand, are optimized for bandwidth and parallelism. They can run hundreds of thousands of threads, but each one of those threads is substantially weaker than CPUs. And unlike CPUs, GPU cores are a lot simpler. They don't have out-of-order execution. They don't do speculation in the same way that CPUs do. And that means that their memory latency is substantially higher, but memory throughput is much greater. Now, there are two ways to program GPUs today. The first is grid-level models, where you invoke GPU algorithms on the entire input. The algorithms are launched from the CPU, but run on the GPU. You don't explicitly parallelize or partition the work or data. The system does this for you automatically, deciding how to divide up the problem and map it to execution resources on one or more GPUs or other devices. In fact, as far as you're concerned as a programmer from your frame of reference, many of these models have the appearance of being sequential. So this is the easiest and most common approach to GPU programming. There are many excellent GPU-accelerated libraries that embody this grid-level programming model, such as CuPy, PyTorch, cuDF, cuBLAS, cuFFT, cub, JAX, etc. Libraries should be the first thing that you reach for when writing GPU code. They'll make your life easier, and they'll often give you better performance because they're written and tuned by a team of experts. You should try libraries before writing your own GPU algorithms. For almost every use case that you can imagine, there's an existing library. And if there is, you should try it out and benchmark it. And if it delivers the performance that you need, then just use it. Don't try to reinvent the wheel, because even if you do manage to do better than one of these libraries, whatever work you've put into that will probably become useless in 1 to 2 years, because computer architecture is changing very fast these days. But sometimes there's no library that does what you need, or you've tested and you've found that you just can't get the performance that you need with the libraries that do exist, or there's two different libraries that do two different separate components of things that you need to do. But what you really need is you need those two algorithms to be fused into one. And so that's when you should consider writing your own GPU kernels. So a GPU kernel is a function that is executed in parallel by a group of threads. And all of these accelerated libraries are implemented with GPU kernels. Historically, GPU kernel authoring has been a pretty low-level task that you've had to do in languages like C++ or C. Today, when you write a GPU kernel, you're programming at the thread level. You explicitly code every thread that you run on the GPU. You decide how to split the compute work into blocks, how to divide the data into tiles, and how those blocks and tiles get mapped onto threads. Writing CUDA kernels in this way gives you complete control, allowing you to program and tune every aspect of the GPU. And in each new generation of NVIDIA GPUs, we expose more tools, giving you greater control and freedom. But all of these choices can be overwhelming. It would be very nice to have a higher level abstraction that succinctly expresses kernels and allows the system to select which tools to implement them with, instead of you having to make that choice yourself. NVIDIA GPUs have had tensor cores to accelerate operations like matrix multiplication and convolutions. And every GPU generation since they were released, the structure of the tensor cores has changed. The formats have changed, the precisions have changed, the width and size has changed, the mapping to threads, etc. All of that changes every architecture. And this has forced users to rewrite tensor core code for every new GPU that we release. Then the new GPU comes out, and whatever code you wrote that uses the tensor cores is essentially no longer valid, and you have to start from scratch. And what we need is a middle ground, a model where users explicitly partition work and data, exposing parallelism. But that partitioning is logical, not physical. The system decides which tools to use. It will map the partitioned work and data to threads and execution resources. Because the mapping is implicit, it's portable. The system can pick different mappings for different NVIDIA GPU architectures. So in this approach, we get much of the control and flexibility of thread-level programming, but we also get the high productivity and portability of grid-level programming. And we call this new model tile-level programming. And it is coming to CUDA soon. We have recently announced Coutile, which is a tile-based kernel programming model for NVIDIA GPUs. It is higher level and array-based and automates block-level parallelism and memory movement. We've built it to simplify GPU programming and to improve portability for new hardware features like tensor cores. It is built on top of TileIR, which is a novel, new, low-level compiler stack and intermediate representation for tile programs that we have developed. So cuTile Python kernels are JIT compiled to TileIR using an execution model that allows the code to be executed without the need for a Python interpreter as native code, similar to Numba's no Python compilation mode or other DSLs like Triton or Jack's Palace. So this model has some semantic compromises. All of the objects get mapped down to value or pointer semantics, so there's no reference counting. You are responsible for managing the lifetime of things. And you can't do some Pythonic things like dynamically modified types. And all of this, both cuTile and TileIR, will be released soon. So cuTile is meant to be simpler and higher productivity than traditional CUDA programming. In the traditional CUDA programming model, we call it SIMT, and that's what I'll be using throughout the rest of the talk to differentiate it from this new model. The idea is that you should be able to get good performance faster with tile programming. So with cuTile, you don't have to decide how data is loaded, mapped to threads, and stored locally. The system does that for you. You just express your computation as array operations. So to reach the speed of light for a matrix multiplication before cuTile, you'd have to write something like the CUDA C++ code on the left, which is no easy feat. And it's also not portable. That code that you'd write would change from GPU architecture to GPU architecture. With cuTile, we can write this simple code on the right, which is just what you'd see in a textbook on how to write a tiled matrix multiplication, and you can get good and portable performance. This is what the actual speed of light matrix multiplication in cuTile looks like. cuTile will be exposed first in Python, but a C++ dialect is also coming, which will be intentionally similar to what you're going to see today, but uses modern C++ idioms and best practices. But we're going to mostly focus on what the Python exposure looks like today. So now let's explore how the tile programming model differs from that traditional CUDA programming model. In CUDA SIMT, the unit of execution is a thread. You write functions that are executed by many threads at once, and we call these functions kernels. The set of threads that a SIMT kernel runs on is called a thread grid. It's hierarchical, organized into different subgroups of threads, warps of threads, blocks of warps, clusters of blocks, etc. Users have to define the shape of this hierarchy and explicitly program it and program to each level of the hierarchy. In cuTile, the unit of execution is a block. A block is a group of threads or execution resources that has a single thread of control. You write tile kernels that are executed by many blocks at once, but each block only executes the kernel once on the control thread. In SIMT, the unit of data is individual elements. You write scalar operations on elements that each thread performs. If you want each thread to apply an operation to multiple elements, then you would write a for loop. There are no native array operations in CUDA SIMT. It's fundamentally a scalar programming model. On the other hand, in cuTile, everything is an array. You express block-wide operations on entire arrays. In both SIMT and tile programming, the user is responsible for splitting the computational work into blocks and dividing the data into tiles. The key difference between SIMT and tile is who is responsible for mapping blocks and tiles onto execution resources in memory. So once you've partitioned your work in data, exposing parallelism, there's still a lot of decisions to be made. What elements of data will each thread work with? Where does each thread keep copies of those elements? GPUs have many different kinds of memory available to them. How should those local copies be laid out in memory? The memory layout can have a huge impact on performance. How does each thread load and store those elements from global memory? There are now many different ways of doing this, and they are growing in complexity. And then how does each thread perform computations? And again, there are now many different ways of doing this, and some of these mechanisms are specific to particular GPU architectures. They change when the new chip comes out. In SIMT, the user is responsible for answering all of these questions by picking from the many tools that are available. But in tile, the system makes these decisions. analyzing the program and selecting the best tools for the target NVIDIA architecture. All we have to do explicitly is parallelize by dividing the problem up into blocks and tiles. Within each block, everything is single-threaded, and you just perform array operations on tiles. So let's look at an example. When running a SIMT kernel, each thread within a block will execute the kernel. But a tile kernel is run by just a single thread per block. Within a tile kernel, we create tiles, which are a special type of local array that you can perform array operations on. And those array operations are sequential with respect to the control thread, but they may be parallelized under the hood by the system using the block's threads and other execution resources. So if you know how to use NumPy, you know how to use cuTile Python. So here is an example of softmax written in the left in straight NumPy and in the right in cuTile. cuTile is fundamentally array-based, similar to languages like APL. There are two different kinds of arrays in cuTile. Global arrays are typical NumPy-like mutable arrays that are accessible by all tile blocks. So they're mutable, which means that if you modify their contents, any other references to the underlying data will see the changes. And they are passed in as kernel parameters or globals. You can only perform a limited set of operations on global arrays in tile code. Most importantly, loading from them to create tile arrays or storing tile arrays to them. Now, tile arrays are immutable, NumPy-like arrays that are local to a block. The operations on tiles will always return a copy, not a view, and they are parallelized across the block's execution resources. Most of the operations that you can perform on NumPy arrays will be supported on tiles. But from the perspective of the block's single thread of control, while all those operations are parallelized, from the perspective of the block's single thread of control, those operations are performed sequentially, just like they would be in NumPy. All of CUDA's underlying launch APIs support both SIMT and tile kernels. And this means that users don't have to care how a kernel was written, be it SIMT or tile, to use it. And this means that you can use and integrate tile kernels anywhere that you've been writing CUDA kernels today. So you can use them in CuPy, in cuDF, in PyTorch, in JAX, etc. The array parameters to kernel launches can be anything that satisfies the DLPAC protocol. In Python and C++, it'd be anything that can fit into an MD span. So this could be NumPy arrays, CuPy arrays, PyTorch arrays, etc. Now, tile arrays have value semantics, which simplifies compiler analysis by eliminating problems such as aliasing. And in fact, they have, since they're immutable, they have single static assignment semantics. All tile operations return copies, not views. Now, some NumPy array operations, such as indexing, reshaping, transposing, would typically return you back views, not copy, when possible, to avoid creating unnecessary copies and allocations. But the tile equivalents will always return copies, not views. Assignment to the elements of a tile is ill-formed because they are immutable. If you need to change the value of some of the elements, then you would need to make a new tile. You can do this with the where operation, which would take a Boolean tile and two source tiles and return a blended tile that has elements from the first source when the corresponding Boolean tile element is true, and elements from the second source otherwise. It's a little bit unnerving to think of tile arrays as values. Typically, our intuition is that it's fine to make copies and temporaries of scalars like ints because they are cheap to copy, they can fit into registers, and they won't always be materialized. Every time you copy an int in C++, you don't worry about it because the compiler can collapse the unnecessary copies. But we typically think that array copies should be avoided because they're expensive and that they'll always lead to an allocation and materialization. But tile arrays are different. You have to treat tiles as you would ints. They are cheap to copy and won't be materialized unnecessarily because they are a fundamental primitive in our compiler stack. And so the compiler can see and eliminate unnecessary copies. Imagine a computer architecture where all of the instructions are array operations and all of the operands and registers are arrays. In that sort of architecture, you wouldn't worry about the cost of making these array copies. And this is exactly the tile programming model. So let's look at another example, a tiled matrix multiply in cuTile. So we can create tiles with NumPy-like creation operations like zeros. The shape of a tile must be a constant expression. So something that is either a constant or that the compiler can see comes from a constant. And there's a few reasons for this constraint. First, it creates optimization opportunities. Additionally, tiles may end up being placed in shared memory or some other resource that needs to be statically allocated. Now, this is Python, and we're talking about doing JIT compilation here. So at the time that we're doing JIT compilation, we do, of course, know what the value of all of these inputs are. But we have to decide which of those inputs to embed into the kernels. What this means is which of these inputs, if they change, would cause us to have to redo JIT compilation. And if we redid JIT compilation when any parameter changed, there wouldn't be a lot of point in doing JIT compilation and caching it. This ct.constant type annotation instructs the JIT compiler that this parameter is one that should be embedded into the kernel. So if that parameter ts changes, then we would have to compile a new kernel. You can kind of think of it like const expert in C++ or like adding a template parameter in C++. You change a template parameter in C++, you get a different instantiation of the function. Now remember, the system decides where the tile will be stored. In register memory, in shared memory, in tensor memory, global memory, or even in a combination of different memory kinds. The system will also decide what layout the tile will have. And this is often tied to what elements each thread will be responsible for when array operations are performed. And again, that is a decision that the system will make. For example, during loading, we want a specific memory layout such that each thread is loading elements nearby to elements that their neighbors are loading to ensure that the loads can be coalesced together and issued at once for an entire group of threads, which is essential to get good performance on GPUs. Today, each dimension of a tile must also be a power of 2. And this is a constraint that we expect to have at launch but plan to relax as soon as possible. And because we may have to put a tile into all of these different kinds of memory spaces, this is why we have this restriction that the size of a tile has to be known at compilation time, because some of these kinds of memory are statically allocated. We cannot dynamically decide the size of an object that we're going to put into the memory kinds. Remember that a block invokes a kernel just once on its control thread. Scalar operations in control flow are going to be executed just a single time. Tile load operations create a tile by copying a part of a global array. Load and store operations are indexed in the tile space. The tile space of a global array is the index, is the multidimensional space of tiles into that global array of a certain tile shape. So a tile index I, j, etc. with shape S refers to the elements of the global array that belong to the ith, jth tile of that shape. If we provide a different tile shape, then the tile indexing will be different, and we will load a tile with a different set of data, even if we're using the same index because we're in a different indexing regime. Remember, the distinction between blocks, subgroups of threads, which are a unit of execution, and tiles, subsets of global arrays, a unit of data. A block may work with multiple different tiles with differing shapes originating from differing arrays. The load and store operations are a portable abstraction over the many different strategies for memory movement that are available in CUDA today. For example, load could lower to a traditional synchronous instructions that are executed by every thread, potentially vectorized. Or it could use the asynchronous thread copy instructions available in newer GPUs, allowing memory movement to be overlapped and pipelined with compute. We could also use the Tensor memory accelerator to perform asynchronous block-wide loads and stores, allowing for even more overlap of compute and I/O and exposing much greater bandwidth. The system will pick the best option available given the constraints of the memory access patterns that you've specified and the hardware that you are running on. Next, we have a matrix multiplication. And here we use a matrix multiply accumulate operation unique to cuTile Python. But we would also have the NumPy equivalents map, mul, and dot. But there are some cases where we have to introduce our own versions of operations. For example, in the case of MMA, to be able to expose precision flags and controls that are not present in NumPy. MMA, map, mul, and dot are all abstractions over hardware, this time over compute hardware. Remember earlier we talked about the differences in formats, precision, width, and mapping to threads for tensor cores across NVIDIA GPU architectures. With cuTile, you don't have to worry about all of those changes. You can write tile code once, and the system will take care of mapping it to both current and future tensor core hardware. So this is the story for how you can portably program tensor cores going forward. Then finally, we have a store, which writes a tile into a subset of a global array. Another way to perform loads and stores is with views. View objects produce new tiles from an input array or a tile. A partition view represents the tile space of an array under a particular tile shape. You index a partition view with a tile index, which loads the tile at that index from the array. You can also assign to a partition view index to perform a store. In a kernel like mapmul, where you are loading multiple tiles of the same shape from an array, this can be more concise and cleaner than calling load. Some examples of other types of views would be an overlapping view that would allow you to get overlapping pieces of the input to do something like a stencil or convolutions, or a view on another tile that allows you to get a subset or a slice of that tile. So here's another demo, a non-causal flash attention v2 forward kernel. For a load, we can specify the memory layout of the input global array with the order parameter, which takes the NumPy style argument F for column major or C for row major, which is the default. Now note that this only specifies how the global array is accessed, not the memory layout of the loaded tile, because that's up to the system and cannot be controlled by the user. We have operations for combining tiles, cat, subdividing tiles, extract, and reshaping or casting them. Tiles support NumPy style broadcasting. When operating on two arrays or an array and a scalar, the shapes of both are compared element-wise, starting with the rightmost dimension and moving leftwards. Two dimensions are compatible if they are equal or if one of them is 1, in which case the dimension will be stretched to match the other. One of the objects may have fewer dimensions than the other. If so, then the missing dimensions are assumed to be 1, meaning that they will broadcast. So at launch, cuTile will support a wide range of numeric D types. Arithmetic floating point types and all non-floating point numeric types can be used with all arithmetic and mathematical operations, such as addition, subtraction, trigonometric functions, and transcendental functions. Restricted floating point types can only be used with certain operations, such as matrix multiplication. In terms of promotions, our system of promotion is more similar to PyTorch than NumPy. NumPy prefers to promote in ways that are always safe. For example, adding a NumPy array of int32 or multiplying a NumPy array of int32 with another NumPy array of int32 can promote to int64, which can have a big performance impact. So we never promote within a category. Our promotions tend to prioritize performance and are a little bit closer to the promotions that you would get in C++. We also disallow many implicit conversions that frameworks like NumPy would allow. You can write and use SIMT and tile kernels in the same source file. We also plan to support hybrid kernels where you can write both SIMT and tile code in the future. Llama 3.1 is an open source language model developed by Meta, and we ported Llama 3.1 inference to cuTile, and we're able to get about 93% of the speed of light, which is cuDNN's performance. And this was with our very infant tile compiler. Performance will only get better from here. But cuTile isn't just for large language models or machine learning. This extends the CUDA model and applies to GPU programming in all domains, from HPC to data science to computer vision. In just a couple of weeks, we were able to port Miniweather, an HPC mini app for 2D viscous fluid flow, to cuTile. It's a traditional HPC stencil code on a structured grid with a bunch of different physics models, which are shown here. And it doesn't actually use the tensor cores at all. However, it can still benefit from cuTile because cuTile will automate things like using more advanced memory movement operations like those block-wide loads and stores, which would be very challenging to program manually. We envision expressing stencil kernels like those used in Miniweather like this. Each block loads one overlapping tile of elements from the global array and then creates a stencil view to that tile. The stencil view can be indexed with relative coordinates, producing tiles of the same size but with the contents shifted. And this allows us to perform operations on neighboring elements. When storing the result, we only want to write the interior points of each tile, so we mask away the other points. Those points will be computed and written by the neighbors. So cuTile is a major new addition to CUDA. It is the first time that we've extended to a new programming paradigm. But SIMT programming isn't going anywhere. There are some things that you simply cannot express in cuTile. It is fundamentally a data parallel array-oriented model. So things like synchronization algorithms, where threads within a block must explicitly communicate, or sorting algorithms, etc., you would probably not be able to implement efficiently in cuTile. cuTile is meant as an addition, not a replacement. We're very excited about the possibilities that cuTile unlocks, both for Python users and also for compiler authors and other languages that might want to target tile.ir. This will make it a lot easier to write speed-of-light GPU kernels that are more efficient and safer. If you want to learn more about GPU programming, there are many talks available to watch on demand from GTC 2025, NVIDIA's developer conference. We've also released a new open source CUDA curriculum with tutorials, notebooks, and other learning materials, which you can find on our accelerated computing hub on GitHub. We've also got lots of great courses in NVIDIA's Deep Learning Institute on CUDA and parallel programming. And as a thank you for attending today, you can access our course catalog for free for the next 6 months using this QR code. Don't worry, all the links will be on the last slide. And if you're interested in parallel programming, algorithm design, and programming language development, my buddy Connor and I have a podcast, ADSP, Algorithms Plus Data Structures Equals Programs, available on all streaming platforms. We also do have stickers. We promised we would have stickers. The stickers are here. You can go subscribe now. One of my favorite episodes, we interview Sean Parent, pictured here, and he tells us about the time that he was working at Apple, for some reason was given an Apple corporate Porsche. He crashed it, thought he was going to get fired, and then Steve Jobs came in and saved him. So here are all the links, as I promised. And thank you all for your attention. We've got a good bit of time if we want to do some questions. And remember, I have rulers that if people ask good enough questions, I'll give them out. Can either Connor or Ashwin write down the questions? Because I like to have the questions recorded for later. So I'll give him a second to get his phone out. We'll start with Vittorio.
So one of the things that I found annoying with C++ algorithm is that when you chain them together, it kind of like has to finish the first one, then the second one, then the third one, and so on. I'm guessing with this approach, because you're compiling the kernel, it's going to be like a pipeline for each thread, right? They can combine the other.
Yeah. So you do not have the fork join that you have with the grid level models. That's the real downside of those grid level models. If we go back to here, we're getting there. It is like the first couple slides, so, It's like when you had to rewind the VCR. Whoa, that was a little bit fast. Yeah, so those grid level models, the sort gets launched, then the cumulative sum gets launched, then the divide gets launched, then the sum gets launched, etc. And because it has these seemingly sequential semantics, it's really challenging to take this and to turn it into something that's fused. In particular, these sorts of models, things like CuPy or Thrust or PyTorch, these are eager models. Another example would be pandas, if anybody's from the data science framework. So these are eager models. The semantics are that when you invoke one of these things, it gets launched immediately. If you have a model like this, but it's lazy, where you should create these operations, but then you have to explicitly launch it or something, then it becomes easier to deal with this. And pretty much all of these frameworks that are widely used, they have some form of compiler that tries to take this code and compile it in a way that fuses it. So CuPy has CuPy Fuse. PyTorch has like 5 of these different of these things. Everybody's got some form of graph compiler like this, but it's a very challenging problem to get this right. The advantage with the tile level model, this right here. The advantage with tile level is that you're still writing a kernel. You are still programming. You're still writing something that's going to be cooperatively executed. So it's much easier for us to do the fusion because the semantics are that this is something that's executed by every block. And the compiler under the hood will do all sorts of fusion and optimizations. And that's sort of really the selling point of this is that we've crafted a DSL that has very nice semantics. It's all value semantics. It has a very simple type system. And because of that, it allows us to do optimizations that would be very challenging to do in just like regular C++. And in the C++ form of this, we're still sorting out like what the aliasing rules will be, but the C++ form of this, when you write one of these C++ kernels, you'll be writing value semantic code. And because of that, we'll be able to do those optimizations in C++ as well. Yes, Victor.
So I have two questions that are related to each other. Since you mentioned that the system orchestrates the tile layout and how this computation is scheduled, my question is, how do you handle determinism in this context, and how do you handle debugging tile-based programming in the context of replay?
So this is a good question. TileIR supports both ahead of time and JIT compilation. If you're running again on the same architecture with the same inputs, et cetera, it is almost certainly going to give you the same layouts. The configurations and the tuning are not based on any dynamic metrics. It's based on what is your code doing in static analysis. So all the decisions are made on static analysis of the code and information about the environment. And you can do ahead of time compilation so that you can get a binary where you can profile it and where you can look at what the actual layout and structure is. Almost all of these decisions are decisions about like the major decisions are more so about like hardware capabilities, like what architectural generation you're on. That said, one thing we didn't touch on, in a lot of these examples here we're calling the parameter R, you have to pick some size for how big is the data in each block going to be. And the question becomes, how should you make that decision? Because it's sort of a logical decision, too. You could pick a really big size, and then the compiler could decide that it's going to pick a smaller physical size under the hood. The guidance that we're giving people for this is that the best practice for these knobs will be to do auto-tuning. There are also some explicit performance tuning knobs that we expose programmatically. One of them is like an unrolling pipeline depth. And then there's another one called latency, which is a number between 1 and 10, which is how memory bandwidth heavy you think your application is going to be. All of these parameters are sort of designed for auto-tuning. We don't have an auto-tuning harness in place yet, but other frameworks in this space, like Triton, come with a built-in sort of auto-tuning harness. So we'll probably provide something like that. And that's what we recommend. It doesn't have to be online auto-tuning. It doesn't have to be something that you do every time you run your program. But our recommendation is at least that when you know what the environment you're going to be deploying on, run the auto-tuning framework. It'll spit out some, configuration and then ship with that configuration. And we're seeing a big shift towards two things. One, JIT compilation, and two, auto-tuning. Historically, the way we've shipped software has been that we pre-compile and pre-bake a bunch of configurations. So something like cuBLAS, our linear algebra library, we compile, 1,000 matrix multiplication kernels, and then we ship them to you. And that's why the binaries are very big. And then the cuBLAS decides when you run some input, which of those 1,000 kernels it's going to use. The problem is that if you look at the direction that hardware is going, like the next architecture, you'd need 10,000 kernels. And the one after that, you'd need 100,000 kernels. And at some point, you'd get to like, okay, now you need to have a 100 gigabyte library. So it's not practical. And it's not practical to cover the entire parameter space with pre-compiled code now. And so we're starting to shift towards more JIT compilation, not just to support dynamic languages, but also for statically compiled languages to offer better performance. With the hope that users will be able to tolerate a little bit of startup JIT latency to get that better performance. And because of this means that almost all of our libraries are moving towards auto-tuning, because if you're going to do the JIT compilation, you might as well do the online auto-tuning. Other questions? I saw some other hands here.
Stupid question, but in what situation will a classic CPU be better than a GPU? Let's say you have a data set of 10,000 entries. Are there any situation where you would use classical CPU rather than GPU?
Well, let's look at a slide. Where is? There it is. Take a moment to open it up. Don't need that. That slide actually used to be in this slide deck. I'm not sure why I took it out. There we go. Okay, so you need a sufficient workload to see a benefit from using GPUs. If you try to sum up 1,000 ints or sort 100 floats, you're not going to see a huge speed up from parallelizing that with a GPU. You pay high fixed costs for moving data to the GPU. And so that's really what hurts you, is that you have this high fixed cost to transfer the instructions and the data from the host to the GPU. Your workload is defined by how much compute you're doing per element, which we call the operational intensity, and how many elements you have. A good rule of thumb is that if you're doing O(n) compute, if you're doing 4 adds per element, or applying a function to each element or summing them up, then you typically need gigabytes of data, or at least gigabytes of, or millions of elements to really see a benefit. If you're doing more than O(n) compute, or if your O(n) has a really big constant factor, so if you're doing something like sorting or matrix multiplication, which is n squared, then you'll see speed ups with less data. So that's the typical guidance we give for the sort of cutoff point. The other thing is that when you're starting to GPU accelerate your application, you have to keep in mind that the fixed costs that you're paying them just once for every time you go to the GPU. So a great example, there was a talk at PyCon this year where somebody was talking about using our accelerated data science library and examples of where sometimes using GPUs was a gotcha and you didn't get better performance. And they were showing something where the workflow was do some CSV parsing, do some data science, and then do some CSV output. And they moved the data processing part to the GPU, and they didn't see a speed up. And one of our engineers was in the audience and was like, hey, wait a moment. And he went and wrote what they were doing himself in a notebook. And then they just moved the parsing of the CSV and the writing of the CSV from the CPU to the GPU. And that led to seeing a speed up over the CPU instead of not seeing a speed up. And the reason is because there was no additional cost for moving that operation from the CPU to the GPU. Since you were already doing that data processing there, the next stage of the pipeline was already there, you're not paying for another transfer. And you'll see a speed up from doing that operation. You see a speed up from doing that CSV parsing on the GPU. It might not be worth it if you were only doing the CSV parsing to do it on the GPU. But if you're going to do that and then do something else, once you decided you're going to do something on the GPU, moving as much of the pipeline as possible there to minimize transfers, to keep the compute local to where the data is, that will have a big impact. All right, other questions? Yes. Why the strict immutability on tiles? Are there optimizations we can't perform? Yes. So in most compiler frameworks, most compiler frameworks like LLVM and MLIR, which we use a single static assignment model, where when you assign to a variable once, and its value does not change. And that unlocks many, many types of optimizations. When we were designing cuTile, we had to very carefully decide which things were going to have a one-to-one mapping down to the IR. And we decided that that tile objects were going to have a one-to-one mapping. So the tile objects directly map down to tile IR SSA values. If you know that, like conceptually, if you know that something is never going to be changed by anybody, then it's very easy to say eliminate unnecessary copies or do dead code elimination or fuse operations together because you know that there's no other observers. Like, you know that I uniquely own this value, nobody else is looking at this value, and anybody else who like has touched this value, they've only ever made a copy. No, there are no references to this thing, so I can do whatever I want with it. So it does unlock a ton of optimizations. Additionally, because you can only get it by value, you never have an aliasing problem with tiles. And yeah, so it just there's a ton of things that it unlocks, and it's fairly fundamental to the underlying model. Now, question in the back?
What happens in a situation where we have irregular computational patterns like PI, so that that will shift some of the computations, but if, for instance, in the example of the image, I can divide into equally sized tiles.
Yeah, so if you need to divide into tiles that are not equally sized, that is a good question. I think that you could either you could either like do sparse tiles where like if you know that you're not going to like you could just create a tile that's larger than you need and just like sparsely access it, and the compiler is able to do some amount of optimizations to, like if it knows that a large part of a tile is unused, there's some tricks that it can do to eliminate that. If there's really a lot of load and balance across different blocks, I think it's very tricky to do that with this model because, again, a lot of the places where tiles live are going to be statically allocated. You certainly can do like random access into tiles, and the tile will have strong support for doing like structured sparsity and things like that. But I think that having tiles of differing sizes within the same block, like within the same kernel, like having a tile of one size in one block and then one size in another block, that's just fundamentally going to break the programming model. Other questions? Yeah.
How does the library deal with data sets that might not fit on the GPU?
First, I'll say it's important to not think about this as a library. It's a compiler, and if you think about it as a library, you may be surprised when it does compiler things. How does it deal with data sets that are larger than can fit on your GPU? I would say that's a separable issue. This is a library just for writing the kernel. So this just takes an I and O, which are some arrays, some global arrays somewhere. And the question of how those global arrays got to the GPU, that is outside of the scope of like what this does. The typical way that you do this, there's a couple different approaches. Firstly, you could use CUDA unified memory, which allows you to allocate memory that can be accessed by both CPU and GPU, and it'll be paged into the GPU. And if you have sparse access patterns, or if you've got a data set that's larger than what can fit, this can be a very good approach, because then you can let the operating system and actually the hardware features that support unified memory do the paging and the movement of your data between CPU and GPU. You can also design a kernel I know I just said that this is outside of the scope of what you can handle here, but you can design a kernel where the kernel will pull in data by batches. And in particular, that works nicely with cuTile because cuTile automates making your data movement asynchronous. So it uses all of these memory movement mechanisms that are asynchronous. And so if you write sequential code in cuTile that pulls in data chunk by chunk, under the hood, the compiler will pipeline that data movement so that while you're doing your compute, the next chunk of data will be loaded in, but you don't have to explicitly program all of that. And that's actually one of the huge things that makes this so fast. So this in this MapMul kernel right here, On the right, on the left, the Matmul kernel on the left is explicitly doing this data pipelining, and that's why it's so long. On the right, we have these passes that do this automatic data pipelining, so that it doesn't look asynchronous on the right here, but that will actually end up being pipelined and overlapping the movement of data from global memory to local memory with the compute. Other questions? All right, well, I think we're about at time. If you want stickers, I also have NVIDIA stickers and ADSP stickers. You can come up here. And I'll be around for just today. I'm leaving tonight at like 9:30. So if you have questions for me, try to find me sometime after this. All right, thank you all.